Good morning, guys. It is Friday. We are on our second day of lecture for gas physics and the gas laws. We will get started on finish up where we were left off yesterday. So get your things together, and I'll pause for a moment to get the screens up, and we'll go from there. All right, guys, we're back. Let's go ahead and get started with the lecture. We left off yesterday talking about the qualities of oxygen. We first talked about the qualities of actual gases, right? Whether they're flammable, whether they're non-flammable, whether they support combustion, and then which ones fall under those categories. But today we're going to focus on the qualities of oxygen, because there's a lot of qualities of oxygen that we must be aware of when we're making decisions on therapy, okay? And so I'm also going to let you watch a video of cylinder making. I'm not going to be able to record that portion, all right? So I'm trying to put that video in when I have more people on so that more people get a chance to see it. If not, I'm going to have to put the video in the link, put a link to that video, and you can watch it on your own. But that will be part of the class today. All right, so let me go and share my screen to the lesson plan. I go back and forth with lesson plan and PowerPoint. They have the same information, okay? But, all right, so the qualities of oxygen. So again, if you didn't get the rest of them, these up here, the qualities of cylinder gases and the safety systems, right? That was in the lecture from yesterday. You'll need to listen to the lecture and fill out your note-taking guide. It follows along just like this here, okay? But today we're starting on the qualities of oxygen. Oxygen is colorless, it is odorless, it is tasteless. A lot of people say, you know, I got oxygen, it has a certain smell. I think you're smelling the actual nasal cannula. The device that goes into your nose, that little plastic, fresh new plastic, I think that's what you smell when you're doing that. All right, but it is colorless. Talking about oxygen, it is colorless, odorless, tasteless, right? It has an atomic weight of 16 grams. And it has a molecular weight of 32 grams. Okay? Atomic weight of 16 grams and a molecular weight of 32 grams. So if you get a question that's got a multiple about, all are true about oxygen, right? Colorless, odorless, it's tasteless. It has an atomic weight of 16 grams. It has a molecular weight of 32 grams. And what about its flammability? What will we say about the oxygen's flammability? Is it flammable, or does it support combustion? Anybody? Anybody remember whether it's is oxygen flammable, or does it support combustion, or is it non-flammable?
Support combustion.
Supports combustion. That will be something that you would put on for your answers. So not only just these qualities right here, but don't forget, oxygen also supports combustion. It's not flammable, but it supports combustion. And anything oxygen is mixed with now supports combustion. So if you take something that was not flammable, right, but you mix oxygen with it, then it now supports combustion, all right? It supports combustion, any kind of mixture. For example, helium. Helium is non-flammable. It doesn't support combustion alone. But if we mix helium with oxygen, it does support combustion. And we talked about those mixtures. So oxygen and helium we would use in order to because we already talked about yesterday, what's different between helium and air? What have you noticed about helium and air? What's the difference?
Helium floats.
Mm-hmm. So it will float because it's less dense than oxygen. Helium is less dense than oxygen. Therefore, it will float inside of a balloon, right? Morning. And so therefore, sometimes we use a mixture of helium and oxygen in order to take the oxygen and lift it up over an obstruction. If you have a tumor in your large airways or something like that, the heliox mixture will help lift the oxygen to go up over obstructions in the larger airways, okay? Helps that oxygen get down into the parenchyma where it's trying to go, but it's being blocked by a tumor, right? And so if we have helium in the mix, then it will lift up over the helium, okay? Lift up over the obstruction in order for the oxygen to get where it's trying to go. What about its temperature? This is very, very important right here. Very, very important about the critical temperature of oxygen. Critical temperature. That means above this temperature, it cannot remain a liquid. I told you we store bulk oxygen in liquid, okay? We store bulk oxygen in liquid, okay? Whenever you have a hospital, it has a liquid tanks outside, okay? Or cylinders, really, really tall, about 2 stories tall, that holds all the liquid oxygen. And then as it goes down the pipes, it raises up above this critical temperature. And therefore, then it changes into a gas. And that gas is then pumped into the walls of the hospital, okay? And so that critical temperature is negative 118.8 Celsius or negative 181.1 degrees Fahrenheit at 49.7 atmospheres. This atmosphere is not that important. Just know that the critical temperature of liquid oxygen is negative 118.8 degrees Celsius or negative 181.1 Fahrenheit. If that liquid oxygen temperature rises above this critical temperature, it cannot remain a liquid. It's going to turn into gas, okay? Now that's very, very important because economically, it makes more economical sense for the hospital to store oxygen as a liquid than opposed to storing it as a gas, because you can hold way more liquid. It goes so much farther than the gaseous O2, okay? Liquid O2 will go much farther economically than gaseous O2, okay? All right. They also use fractional distillation in the process of making the oxygen. Now, let's look at some of the cylinder markings on the actual cylinder. Still talking about the oxygen cylinder, okay? On the front, we have the DOT.3AA 2015 PSI, okay? These are the DOT specifications. On one side of the cylinder is going to have DOT stamp on it, okay? Now, 2015 is the recommended filling pressure. Recommended filling pressure is 2015 PSI. 2015 PSI is the recommended filling pressure, all right? Now, you're going to learn that companies are allowed to overfill the cylinder by 10%, making it a total of 2,200 PSI. At 2,200 PSI is considered full, okay? An oxygen cylinder, no matter what size it is, has the same pressure on the inside, okay? An H cylinder and an E cylinder both are considered full at 2,200 PSI. Okay, that's very important. At 2,200 PSI, both any cylinder at gas, if it's filled with gas, is considered full at 2,200 PSI. Now, when it's first filled or made, when the cylinder is first made, the DOT will stamp that cylinder and say, I recommend you fill this cylinder at 2015 PSI. But by law, they allow the company to overfill that by 10%, which gives it a total of 2,200 PSI, okay? On the front, it also has the serial number of the cylinder. You also have the ownership markings, okay? Whoever, if Kayla has a cylinder factory, then she'll have her little mark on there to let everybody know it came from her factory, okay? It also has the manufacturer's mark, whoever made the actual cylinder. Now, you got somebody who makes the cylinder, and then the DOT has to stamp it, test it, and do all these things. The serial number will be on there, and then whatever cylinder company that's going to retail the cylinders will buy them and put their mark on, okay? To let everybody know this is my cylinder. So, because there are thousands and thousands of cylinders out in use, there's no really way to know which ones are mine and which ones came from my factory or your factory, right? So they have their ownership markings on there as well. All right, what's on the back? Now, these are the things on the front. These are on the front. Now, we got some things on the back. The back of the cylinder will have the original hydrostatic testing date, okay? The date that it was originally hydrostatically tested. It also has some certain specifications on there. The retest dates, right? And the inspector's mark and specifications. So whatever that QC or quality control person is, at the end of the assembly line, before that cylinder is released to the public, it has to be checked. And they will check the roundness of it, make sure it's not out of round, make sure it doesn't have any cracks on the side, the paint is all jacked up or whatever. All of the markings are on there properly, right? Once that's right, he or she will mark his check on there, officially checked and certified. Let it go, okay? Now, as we talked about the cylinders, they have to be filled. They are filled to 5/3 the maximum pressure every 5 to 10 years. That's called hydrostatic testing. What we do is we put it down in some water, right? And then we fill the cylinder up 5/3 to its maximum pressure. If the water is displaced, because if there's a crack in that cylinder or anything like that, if it's weak, if that aluminum or metal or whatever is used is weak, when they fill it up, it will bulk out, right, on one side. And the way we know if it's bulking out is if the water is displaced, right? Any little certain move inside that cylinder is going to make the water move, right? And so that's called water displacement. So that's why it's hydrostatic testing, because remember, hydro means water, right? Just like bicarb mixes with CO2 mixes with, which one is it? Bicarb mixes with water, right? In a process of hydrolysis, right? Because water is being added. So when we hydrostatic test a cylinder, we put it down in this little tub of water, fill it to 5/3 the maximum pressure, and if the water doesn't move, it's good. And that's called hydrostatic testing, which is done every 5 to 10 years, all right? Hydrostatic testing is done every 5 to 10 years. Okay, these are all important information. All right, cylinder filling and duration. I told you, the first time they make it, the DOT recommends that you fill it to 2015 PSI. That's the recommended filling pressure, okay? Recommended filling pressure. All right, so I'm gonna put right here, recommended filling pressure. 2015 is the recommended filling pressure. That's what they recommend, right? After you first make the cylinder, and they say, all right, I recommend you fill it at 2015, but you can fill it by over 10% to 2200 if you want to, right? That kind of puts their hands out of it. So if you do fill it up and it busts in your face, or something happens down the line, DOT can say, well, I recommended that you did 2015, right? That's just the way people do, right? People can say, I recommend you go to this store and not that store. But if you want to go to that store, you can. But then when you go to that other store and you get robbed and killed or shot, they can say, well, you can't say, well, he told me to go to that store. No, I told you I recommend you go to this one, right? I just said you can if you want to. All right, so they kind of free their hands up. You know how people do. All right, so that's the recommended filling pressure, 2015, but they let you go over. All right, they let you go over. Now, you can be overfilled by 10% to hold 2200 PSI. That's considered full, okay? All right, every cylinder, I don't care what size it is, and it's amazing because you're like, well, how can a huge G tank and a little bitty M6 tank hold the same amount of pressure? Because it's gas, okay? Each one, no matter how big the tank is or how big the cylinder is, they're considered full at 2200 PSI, okay? That's full, no matter what it is. All right, now it may go longer. You can use it longer because there's more oxygen in it, but the pressure that gas exerts is the same on any cylinder. It's 2200 PSI. That's considered full, okay? All right, now let's talk about, we're going to talk about duration of flow in a second, okay? Duration of flow, it talks about how long will Mr. Johnson have at the casino, okay? If he's leaving the hospital because he had a little flare up, he got his little medicine, they gave him an oxygen tank, but on his way home, he wants to stop by the casino. So if you know that, you have to tell him how long he has based on the liters per minute or the liter flow that is prescribed by the doctor. The liters per minute of oxygen is a prescription. Oxygen is a gas, it is a drug. It has to have an order. You don't just throw people on oxygen just because you felt like it. You have to have an oxygen order. Now, there's protocols in place where the respiratory therapist or the nurse can put somebody on oxygen if they think they need it, okay? That's a protocol, all right? But that protocol is part of the order. You will have to go back and make sure you put in an order for that oxygen, okay? Because oxygen is toxic at certain degrees. And if you mess around and put somebody on oxygen and you never put an order in for it and they get sick and die, the family gonna sue you. There wasn't an order for that oxygen. Who told you to put it on? Right? You never got an order. And so that can be a problem later on when you're sitting in court, okay? So always have an order for your drugs, and that's oxygen is a drug. So you have to tell him how long does he have, okay? That formula is tank pressure, which is that PSI, times the tank factor. Each cylinder has its own factor, okay? So you have to memorize the factors. And then you divide that by the liter flow, and that will give you the time in minutes, okay? This will give you the time in minutes. Then in order to, of course, get hours, you have to divide that by 60 to get the hours, okay? Basic math. All right, so before we get into the tank factors and the duration of flow, I'm going to show you a video on not hydrostatic testing, but cylinder making, okay? Cylinder making. And I will copy and paste the link somewhere in the chat, in the chat, or in the actual module, so you to watch it, because I can't record it, okay? Because if I record it, it's going to take away my my lecture, okay? All right, so let's take a look. Do a new share. Oh, make sure I got the volume in there. Share, computer sound, optimize, sharing the clip. Okay. All right, again, I'm going to have to stop the recording here, guys, in order for you to watch this video, because copyright infringement. Always handle cylinders with special care. Now, we watched the video together. If you're watching this later on, I cannot, of course, record it because of infringement, copyright issues. I'll put the link to that cylinder safety video in the chat or in the module, and you can watch it later at your leisure. All right, we're gonna take a break now. It's 8:45, come back at 8:55, or just come back at 9. We'll start back up at 9. We're gonna finish up with some more of the lecture. Come back at 9 a.m. and we will finish up with more of the lecture. All right.
Mr. McCarthy, you're muted.
So we're about to learn how long a tank lasts, okay? How long does the patient have left in the tank, okay? Remember we said a full tank is 2,200 PSI. And you take whatever is in it, because if it's not full, it's going to show you how much is in there. You take the tank pressure times the tank factor and divide it by the liters per minute. Now, the factors. The E cylinder is 0.28. A G cylinder is 2.41. And the H cylinder is 3.14. Now, an easy way to remember H is because the number for pi is 3.14. And I had a student that said she loves her Aunt Hattie pies, okay? She said she loves Hattie pies. And so we know that H is Hattie, right? And then the number for pi is 3.14, so that helps you remember the cylinder factor for H cylinders. Now, you won't see a lot of G cylinders out there, but you do need to know the factor and how to tell how long he has, all right? Because that makes a difference. If you are the therapist and you have a patient that, you know, came in the ER, has shortness of breath, some type of exacerbation of COPD, or maybe he's just now finding out he has COPD or has some kind of issue where he's going to have to be on oxygen at home now, okay? That makes a difference. A lot of people have problems with that. You know, that's a big thing to have to go home on oxygen, all right? That's a whole different lifestyle you're going to have to lead, because now you have to carry around an oxygen tank everywhere you go. And so some patients do it all the time. I have been doing it for years. And some patients it's new to them, okay? And so you have to be able to explain everything about the cylinder, about how long they have before they need to change tanks, right? And get another cylinder. So if you got a patient, depending on where they're going, because what if they're leaving Baptist Hospital and they live all the way in Corinth, Mississippi, and they're getting ready to drive home, or they're getting ready to go back to Arkansas or something like that. You need to know how long they have on oxygen. before they run out, because you don't want to tell them, you know, they have a 3-hour trip and you give them enough oxygen to last 1 hour. Well, the last 2 hours, they're going to be out of oxygen. They're going to stop at a hospital or an emergency room, okay? Cannot be without it. And so you have to know what you're talking about when you're talking about how long will the cylinder last, okay? So those are the factors there. You need to write those down, because I'm going to stop the share and show you an actual cylinder up here, okay? So E cylinder, 0.28. A G cylinder, 2.41, and an H cylinder, 3.14. So get your calculators ready, because I'm going to put some scenarios on the board and say, okay, you have this amount left in the cylinder and they're on this many liters. How long will he have in hours? When you do this formula, guys, it's going to give you the answer in minutes. You'll have to convert those minutes into hours. So 120 minutes is 2 hours, okay? Because there's 60 minutes in an hour, all right? Now, one thing that's important, always round down to the lowest hour. So if it says he has, if you figure it out and it says he has 2.5 hours, tell him 2 hours. If it says he has 3.5 hours, tell him 3 hours. Or 3.3, it's 3 hours, okay? 1.5, no, 1 hour. Always err on the side of safety, okay? If you tell him he has 2 hours and 30 minutes, he's gonna stay on that slot machine for 2 hours and 15, right? And think, okay, I got 15 minutes to get home. That type of thing. Just say, no, you just got 2 hours, okay? And that way, that forces the patient to change that cylinder out, okay? Because if they be somewhere stuck without oxygen, they can go into hypoxic respiratory failure, all right? Got to have oxygen, because if we don't have oxygen, our body continues to metabolize carbon dioxide, and that produces what? I said if we run out of oxygen, our bodies will continue to metabolize using CO2. And so if we're metabolizing using CO2, what does that produce?
Hypoxemia.
Good. Lactic acid. Good. All right, and that can kill you. That can put you in septic shock. You can go into become septic. All right. And so that's not what we want, all right? So you have to have that oxygen. For whatever reason they have, you know, when you get a disease process, you don't always come back around, right? Sometimes the disease process is far gone. You have to stay on oxygen. Your body no longer is able to produce the amount of oxygen your body needs. That's why they go home on oxygen. Or look, we call it supplemental. They're on supplemental oxygen. Usually really small flows, like 2 liters, 3 liters, 4 liters at the most. You don't really see a lot of people on 6, 8 liters. That's a little too sick to be at home, okay? But use like 2 liters, COPDers and stuff like that, they'll be on like 2 liters to keep them, because we want them to be hypoxic, but not super hypoxic, okay? Remember that. COPDers live out their peripheral chemoreceptors, so they respond to being hypoxic. That's what makes them breathe, but not 60. Right, we ain't talking about a P little AO2 of 45. We ain't talking about that. That's, if you withhold oxygen from that patient, that's a travesty. Okay, you want them to be mildly hypoxic, but not severely hypoxic. Okay, and so if you put them on 2 liters and they're sat in about 93, 94, that's good. You don't want them 100%. Okay, if they're on 4 liters and they 100%, cut them down. He doesn't need to be 100%. All right, so that's that. So let's look and see how long. Now I don't have the oxygen. I got the medical gas, which is just room air, right? But the factor still remains. All right. This is an H cylinder. Okay. H cylinder, which what is the factor for an H cylinder? 3.14. All right. So let's see how long Mr. Johnson had. Why don't I still hear music? All right, so let's look at it. This is a medical gas cylinder. I'm gonna pull up this thing so it'll be easier for people on the camera to see the actual pressure left inside the cylinder. All right. So when I cut this on, guys, let me cut this off so it doesn't blur on. Put a little light on it. All right, you should be able to see that. All right. So it's at 0, okay? And we're looking at the red numbers. I don't know if you can see it that good, but see the red numbers? 500, 1,000. See that? Okay, we're looking at the red numbers, which is, who got this paper on here? 500, 1,000, 1,500, 2,000, 2,500. Remember we said, what did we say was full? 2,200 PSI. This is in PSI. This is one of our board-on gauge. This right here is considered to be a board-on gauge. This is the regulator, right? Which regulator safety system is this with the nipple and threaded nut? ASSS for the big tanks, right? The larger tanks above E tanks. Okay, you can remember saying the big ass tanks, okay, ASSS, the nipple and threaded nut, okay, goes on to the 8-cylinder. Then this is the regulator here that regulates the pressure, okay. The regulator, we're going to learn, brings the pressure down to a standard working pressure of 50 PSI. So the pressure inside here now is 50 PSI. This is the board-on gauge that reads how much pressure is in the cylinder, okay? And this is the flow meter. This gives us the liters per minute that the patient is on, okay? This is the cylinder. This is the regulator here with the nipple and threaded nut, representing the American Standard Safety System, okay? Then this is a flow meter here. Called the Thorpe Tube flow meter, and I will put my nasal cannula right here connected to my nose, okay? So we got the 3 safety systems going on right here. First one is color coding, right? It's yellow. Yellow means it is what? Medical gas, just medical air, which is room air, okay? And then the next safety system we have is the ASSS, right? Which is the connection right here. The nipple and threaded nut, all right, for the larger tanks, high pressure. Then we have the Thorpe tube with the flow meter, and then what did I say this was? Everything after the regulator is the what? DISS, good. The DISS, all right, which leads to all of my little equipment, okay? So all of those things are in play right here, okay? Now, if I was colorblind and I needed an oxygen tank, I wouldn't know if this was oxygen or not. But the flow meter for the air won't fit on the oxygen cylinder because of this right here is going to be a different size. So if I got an oxygen cylinder, if I have an oxygen regulator trying to put it on an air cylinder, it's not going to fit. It's going to be too big. Even though it's the same ASSS, the size right here is different. Okay, it's not going to screw on. Okay, let me know. Hey, this is not the right one. Okay. All right, so let's see how long we have. Now, here go my factors here. E cylinder is 0.28. The H cylinder is 3.14. And the G tank is 2.41. The formula is factor times PSI divided by the liters per minute. That's going to give me an answer in minutes, okay? I want to know if you have a whole lot of minutes, convert them to hours. Don't tell me, oh, he got 2,000 minutes. I don't want to hear that. Give me the hours. And if it's a long time, more than hours, then if you have, say you have 42 hours, then I'll convert that to days by dividing that 42 by 24, right? and that's how many days I have. If he has 1,000 hours, I can convert that to weeks by doing 24 to get the days and then dividing that by 7 to get the weeks, right? Because it's 7 days in a week, okay? All right, but we'll work them down. Now, how long does Mr. Johnson have? So let me cut the cylinder on to see what pressure is in here. See that? I cut the cylinder on, and that pressure is about, how much pressure is that?
1,500.
Yeah, it's about 1,500, maybe 1,400. Well, let's go with 1,500. All right, so it's 1,500. And this is a 8-cylinder, and let's see, let me cut the flow on. He's on 3 liters per minute. See that? The ball is right there at the 3. See that 3? You got 1, 2 liters, 3 liters, 4 liters, 5 liters, right? I have him on 3 liters. The ball will sit right in the middle of the line, showing me 3 liters per minute. Okay? All right. So he has a, work it out. 1,500 PSI running at 3 liters per minute. How long does he have? Now you give it to me in hours, you give it to me in days, depending on how much it is. His power went off, because usually nobody's walking around with one of these, okay? This is the one that they have in the house. They have their little e-cylinders with them when they're riding around in the car and traveling. But at home, you have this, just in case the power goes out from a storm, right? The storm knocks the power out, then you got to back this up until the power comes back on, because when the power's on, you use a machine called the Concentrator. It plugs up to the power, and it makes oxygen all day long. But if the power's out, that's not working. You have to go hook up to your H tank until the company can bring you some more E tanks or till the power comes back on. Okay, so I want to know how long, and let me work it out too. If you got it in the chat, you can write it in the chat. But I want to know, how long does he have? Okay, how long does he have on this? Pause the video while y'all working that out. Save space. All right, guys, let's work it out. It's the factor, which is 3.14, times the PSI, which is 1,500, divided by 3. So 3.14 times 1,500 equals 4,710. So that's 4,710 divided by 3. 3. That gives us 1,570 minutes, right? 1,570 minutes. But of course, you wouldn't tell your patient that. Mr. Johnson, you got 1,570 minutes. Get on that slot machine, right? You're going to break it down. So let's break it. If that's 1,570 minutes, I want to break it down to hours. I divide this answer by 60, because there's 60 minutes in every hour. So take that, divide it by 60, and that's 26.16 hours. So you would tell the patient he has 1 day. Because if I divide that by 24, which is 24 hours in a day, you get 1.09 days, right? You won't tell them you got 1.09 days, just say you got a day. Mr. Johnson, you got about a day left on that tank. That's running at 3 liters. He has a day left on that tank. Okay? All right. Let's do another. You got another patient who has the same cylinder, and he's running at 10 liters per minute. 10. He's on 10 liters per minute. How long does Steve have left on the actual cylinder? Okay. 1,500 PSI times the factor, which is the 8 cylinders, divided by 10 liters per minute. Right? good. While you work that out. 10 liters per minute, 1,500 PSI on an 8-cylinder. I got a couple of answers that are right. Ms. Thomas, how long does Mr. Johnson have on this cylinder? Good, Miss Thomas. All right, let's get it. So the answer is 7 hours. If you got 7 hours, you are correct. We said tank factor is 3.14 times 1,500. Right? That gives us, what, 47 something? What? Divided by 10. All right, liters per minute. Okay? 3.14 times 1,500 is 4710 divided by 10, which is 471. 471 minutes. Okay, 471 minutes. But we're not going to tell them that, right? So we divide that by 471 divided by 60, because there's 60 minutes in every hour. So let's see how many hours he has. 7.85. So that's almost 8 hours. But I would just say, look, you got 7 hours. Okay? You got 7 hours. Now, if you put, because 7.8 is farther than, it's almost 8. So some people might have said you got about 7.5 hours, right? But I would say 7 to be on the safe side. Okay? He got 7 hours. That way, if he gets home in 7 hours, he still got a nice little cushion before he needs to change. Okay? All right. So let me move this one out the way. And let's say you have this is what you have now. Now you have Mr. Smith. Mr. Smith is on 4 liters per minute on a G tank, right? That is full. How long does he have? Mr. Smith is on 4 liters per minute. He's on 4 liters per minute at home. His power has gone out, okay? Mr. Smith had a major storm. His power is out. His concentrator does no longer work. So he has to hook up to his G cylinder. All right, he has a G cylinder at home, okay? And he's on 4 liters. That's his prescription, 4 liters, 24 hours a day, okay? How long does he have if that G cylinder is full before the firefighters have to get there, or before the power comes back on, or your home medical oxygen company has to come bring him some more tanks? How long does he have? All right, Ms. Rose has an answer. Good, Ms. Rose. Good, Kayla. What you got, Ms. Thomas? off by a little bit, Miss Thomas, but the answer should be 22 hours. 22 hours, because the answer was like 22.09, so that says 22 hours. So what we did, we said G cylinder is 2.41. So 2.41 times, we said it's full, right? A full cylinder is 2200. So 2.41. 2.41 times 2200 is 5,000. Well, that's going to be divided by, he's on 4, okay? It's 5,302 divided by 4 is 1,325.5 minutes. Okay, now I'm not going to tell them that, so I'm going to divide that by 60, and I get 22.09, or just straight up 22 hours. You see what you did, Miss Thomas?
Yeah, I just got a crappy calculator, so.
Oh, okay. All right, let's look at another one. What if Mr. Smith has a, let's say he's on 2 liters per minute on a full E cylinder? How long does he have in hours? The answer you get for this is always that. This is the most one you're going to see, because most people leave the hospital on 2 liters with an E-tank. So you'll remember this one. It's always the same, about the same many hours. You can just tell them that without working it out, because it's what you're going to see 90% of the time. Your patient goes home on 2 liters per minute on an E-tank. Good, Kayla. Good, Miss Thomas. Excellent. Miss Rose, good. 5 hours. So without even working that out, it's 5 hours. Always remember that. When they're on 2 liters per minute on an E-tank, if it's full, it's going to last 5 hours. You're going to tell them, hey, you got about 5 hours to get home. Okay? So now the next question I'm going to ask you makes you think a little bit. All right? And then after this one, we're going to go on to the lecture. What if I have, this is what I want to know now. Mr. Jones lives 14 hours away. He is on 3 liters per minute on a E-tank. Okay? How many tanks will he need for his trip home? How many tanks? I'm going to pull a little closer. Mr. Smith lives 14 hours away. He's on 3 liters per minute and he uses E-tanks. How many tanks does he need in his trunk to last for his trip home? How many cylinders does he need? Oh, you already did it? Okay, let's see. Got one answer. And these tanks are full now, okay? These tanks are full. I didn't write that, but the tanks are full. How many full tanks does he need? Ms. Rose, look at it again. That's not enough. Ms. Thomas, you got too many tanks. Don't need that many. How many tanks does he need to get 14 hours? He's on 3 liters per minute on an E tank. How many tanks will he need to last 14 hours? Kayla, I think yours is right. First, find out how many hours he has on one. And then how many of those will you need to get to 14? Ms. Thomas, I think that's right. Much better. You see, that was you was way out one. You trying to send him to the moon, man.
I wanted to make sure he was well supplied.
Yeah. Yeah, he ain't gonna never run out. What you think, Ms. Rose? Not sure? Okay, let's look at it. All right, 14 now, how long ago? Okay, 3 liters per minute on an E tank. So, scoot up. All right. E tank, 0.28 times 2200, right? Divided by 3. Well, 0.28 times 2200 is 616, right? Divided by 3. And make sure 2200 times 0.28 is 616 divided by 3 is 205 minutes, right? This is 205 minutes divided by 60 is yeah 205 divided by 60 is 3.4 hours. So I would just say 3 hours, right? He got 3 hours per tank. And so how many tanks does he need to get to 14? Well, 3 times 3 was just 9 hours. 3 times 4 is 12 hours. 3 times 5 would be 15 hours. So that's what you say. He needs 5 cylinders. Okay? And that way you can say, okay, Mr. Tank, how long is your drive? I gotta drive 14 hours to get home. right? We'll say, okay, well, let me go out here and factor it up, put 5 E-cylinders in his trunk, or 4 in his trunk and the one that he has, right? And he's good, okay? That's duration to flow, guys. All right, so let's take another 10-minute break. It is 9:45. Come back at 9:55, and we're going to continue on with the lecture. Okay, guys, we're back from break. I just showed you guys a sample of where these numbers are coming from, right? The E-cylinder, if you take the cylinder factor, which is 0.28 times 2200, you get this 616 right here, right? That's where these numbers are coming from. When you do them more and more, you'll see them come up. These same numbers pop up a lot. The G-cylinder, which is 2.41 times 2200, will give us 5308, right? Starting out. Then you got to divide, of course, by the liters per minute. The 8-cylinder, 3.14 times 2200 would give me 6908. But neither one of these make a difference on the fullness, okay? Doesn't matter how big the tank is. If it's full, it's 2200 PSI, okay? Now, there is something called a safety factor. That's very, very important, okay? A safety factor. Now, some regulators or some tanks come with a safety factor implanted just to help with that cushion. And so if they say, for instance, I'm gonna put it in the chat. Well, I don't know if y'all can. Do y'all see the chats when you look at the video, the lectures later on? Okay. Well, a safety factor. So I'm gonna write it down because I want everybody to know. It's just one, we're gonna do one. Safety factor is just a cushion, okay? And all you do is subtract the safety factor from the PSI. So if you have a E-cylinder with a safety factor of 500 PSI, okay? Then what you have to do is subtract that 500 from how full it is. So say you have an E-cylinder with a safety factor of 500 PSI that is 2200 PSI full, right? And they want to say, they're telling you that the patient is on 2 liters per minute. How long will it last? But before you do your setup, I'm just going to show it to you right here how you set it up. Okay, sometimes you have what's called a safety factor. All right, you have don't worry about this, this is not what I'm talking about. An E-cylinder with a safety factor of 500 PSI, okay? And it is 2200 full, it's full, a full cylinder, right? And it's running at 2 liters. How long will it last? Well, what you have to do is the factor times PSI minus the safety factor, okay? Divided by liters per minute, okay? The factor, cylinder factor, yeah, this is the cylinder factor times the PSI minus the safety factor, okay? So how long will that last? It's a full cylinder. It's full, but it has a 500 PSI safety factor built into it, okay? So you have to do the cylinder factor. So this will be the cylinder factor, right? Times the PSI minus the safety factor. I always do what's in parentheses first. So you have a full cylinder, which is 2200 minus 500, right? Times the cylinder factor. Divided by 2 liters per minute. What's 2200 minus 500? 1700. So what you're going to have down here, guys, is 1700 times what's the cylinder factor for each cylinder?
0.28.
0.28. 0.28 divided by 2. So 0.28 times 1700 is how much?
476.
Okay, so 476 divided by 2 is what?
238.
238 minutes. And that divided by 60 is what?
3.9 something.
How much?
So 3 hours. It was 3.9 something. So I said 3 hours.
So 3 hours. Now look, when I told you what you always want to have, a cylinder, E-cylinder running at 2 liters per minute is always 5 hours, right? But look, if we throw that safety factor in there, now he only has 3 hours, right? So of course we know just because it's a safety factor does not mean it's going to cut off in them 3 hours. It's just trying to be safe. So when he go home and rush home in them 3 hours, he still actually has 2 more hours left, okay? Because we know that an E-cylinder that is full, running at 2 liters per minute, will always last 5 hours. That is the most frequent one you will use. It will always, when they go home from the hospital, they're usually always on 2 liters on an E-cylinder, okay? And that's how they go home. And you can tell them, look, if it's full, you got 5 hours. Now that's if it's full, okay? So he has a full cylinder here, right? 2 liters per minute on an E-cylinder, but that cylinder has a safety factor implanted of 500. And then sometimes it's 500, sometimes it's 1,000, sometimes it's 250, whatever it is. But if you have that, make sure you subtract that safety factor away from the original PSI before you start multiplying, okay? So that's the cylinder factor times PSI minus the safety factor. Then you do your division, okay? That's all it is. It's the same way, you just got to subtract that safety factor first, okay? Get rid of that first. Kind of like alveolar minute ventilation. You got to subtract that dead space out of there before you do the multiplication, right? Same thing. All right, so I want to make sure I got that before I forgot. Because you will have one with a safety factor on the exam. I say it's not hard, it's just another step.
Do we need to memorize the square feet?
No, just the safety factor. I mean, just the cylinder factors.
Okay.
All right, what about handling? Handling is very, very important. Some basic things. You always want to keep it in the carry-on stand. You don't want to have your oxygen cylinder around flames or somebody smoking. Proper technique in attaching the regulators, right? So you have a process in doing the actual regulators, okay? There's a process. And we'll be dealing with that process more on Monday when we're doing the lab, going over some lab things. I showed you the process in the videos on the module. If you watch the lab, you saw me go through the processes. Did you watch it yet? Okay, it's in the module. The lab, it's going to say gas cylinder lab. It's 3 or 4 of them in there, matter of fact. Just watch them all over the weekend. It's going to show you the process, okay? You're going to take the cap off, then you have to turn the gas on real loud. Shh, one time, and you got to say cracking. You got to let people know that because that's a lot of pressure coming out, might be right there by their face, all right? But that's the process. Then you put your regulator on, then you turn on the actual cylinder, adjust the flow, and then you have to leave the pressure when not in use. So let's look at it, okay? Let's look at it. I want you to look at it tonight, but I'm going to look at it with you so that we make sure we get it. Since this is my video, I'm good. All right. Yeah. All right, here we go. share my screen. Make sure that you can hear the sound. Okay. All right, let's check it out. Backed away a little bit, but you can zoom in your camera much as you can. I came up here to the school, to the lab, to kind of show you the actual cylinders. This is an H cylinder. Remember the Hattie Patty pies, so the cylinder factor is 3.14 for the H cylinder. And this cylinder here is the E cylinder. This is the E cylinder, which is 0.28, right? So I'll write them on the board. So remember, we talked about on yesterday in the lecture that you must start off with, so we have an 8-cylinder here. This is the cap that I told you about. See? This is the cap. Alright? Very solid, prevents the cylinder from falling over if that was to happen, the stem being broken. Okay? This is the stem here. From here to here, this is the stem. If something happens and hit that stem, this whole cylinder becomes a missile. Okay, it becomes a missile. So when we get them, the lid is on like this. Okay, the lid is on like this. We must first remove the protective lid, right? And then we have to do, what did I say? Cracking, right? Not right. You have to say cracking. What's going to happen is going to remove any dirt or debris from the orifice of the cylinder, right? So that's what we do. We see that? Turn it on, turn it off. Okay? That blows any dirt and grime and dust from the cylinder. Now, who remembers what type of safety system goes with the cylinder? Right, it's the big ASS standard, right? The American Safety Standard, or American Standard Safety System. ASSS, right? And it is the nut and nipple, right? Nut and nipple. So I'll show it to you closer. This is a regulator for the big ASS tanks, right? Remember what I said, to remember that the big ASS tanks, American Standard Safety System, which is your H tanks and your larger tanks, okay? We have the nipple. This is a nipple here, okay? This is the nipple and this is the nut, okay? It goes onto the thread of the cylinder, okay? Other things, on this side, this is the flow meter. Notice how I can change the liters per minute on this side, right? From 0 to all the way up to 25, okay? All right, this gauge here, which has the pressure, right? The PSI, can you see that? Shows you the PSI, right? Remember, 2200 is considered full. So at 2200, you see it's green and it says full, right? Most cylinders, all cylinders at 2200 PSI are considered full, okay? This gauge and how this needle works, this is called the Bourdon gauge. This needle and how it works to read the pressure inside of the cylinder is called the Bourdon gauge. You'll see it in many different shapes and sizes, but it's all the same concept. It reads PSI, okay? Now, what did I say that the standard working pressure of all cylinders, when we want to bring this 2200 PSI down to what, right? All right, that is the pressure. 50 psi. Standard working pressure is 50 psi. Don't forget that, guys. Okay? Whenever I bring the, where is it at? 2200 psi inside of the cylinder goes into the regulator. This regulator brings that pressure down at all of these ports to 50 psi. Okay? 50 psi. Now I can run my machines, right? So say I have a meta nail. Okay? This is my meta nail. It happens to have an oxygen hookup here, right? It has a thread. Now, this cannot go directly onto the cylinder. It's made that way so that you don't blow the machine or cause a pneumothorax. This machine works off of 50 psi of standard working pressure. Even on the back, it'll tell you. If you can see it, it says standard working pressure 50 psi. Okay? So in order to do that, this has to be hooked up to a regulator, which brings this pressure down to 50 psi, right? This is the magic regulator. All right. This will then screw on to the regulator. Okay? This would screw on to the regulator if this is on the cylinder, and now my machine can work. Okay? Now my machine can work at 50 psi. All right? Now, back to the regulator. We already cracked the cylinder. We took the lid off. We said cracking, open it up, turn it off. The next step would be to thread the actual regulator onto the cylinder. And this is the nut here, right? So just move it out the way. This is the nipple, so you might want to zoom in. This is the nipple. We will place the nipple right into the outlet, move the thread up to it, and just start to thread it on, just like a regular screw. Right? Get it on there. Now, with these cylinders, you must use a wrench. That is not going to be enough to seal this pressure. I'm going to have to use a wrench to tighten it up. These are special made wrenches that are used just for the American Standard Safety System. It fits all of the nuts of American Standard Safety System. Makes it easy for you, right? So I take this, remember I said lefty-loosey, righty-tighty. So I'll bring it to the right a little bit, nice little tug, and I don't have to lay on it, okay? And then I'm ready. I'll turn it on to see if it's tight enough. Oh, so I've turned it on now, okay? I've turned it on, and the pressure is up to, in this tank, about 1,000. So it's about half full, okay? It's about half full. Remember, you turn it all the way left, which is lefty-loosey. You turn it all the way on, and then a half a turn back to the off, right? And that is considered on. We're ready for business now, right? So, let's take a recap. Safety systems on the cylinders, right? First thing is color, right? This is a green cylinder, which means it's an oxygen cylinder, right? Then we have the American Standard Safety System on the large tanks, right? Which is the threaded nut and nipple connection, right? Then after the regulator, what do we call everything that's from here on? Everything after the regulator is the DISS, right? The Diameter Index Safety System. That is for all of the connections after the regulator, okay? Now I am ready to either plug up a pneumatically powered device, right? Or I can hook up, now, before I say that, on this regulator, since it's a large tank, the pneumatically powered machines, which I said means run by air, right, or gas, pneumatically powered. There is no battery, there is no electricity to this machine. It's run by gas pressure, okay? So, if you notice, they have little, the two places where you would hook this up to has two little spots inside that show you the 50 psi. So if you listen real close, I'm going to press the little needle inside of here. Hear that? That is for your pneumatically powered devices. The third one is what I would screw an actual binasal cannula to. It doesn't have the little needle inside here. It's just like letting the air out of your tire. You know, you have. All right, guys, make sure y'all listening to this. I know you got about 10 minutes left on it, but this is very important because this is how you're going to do your lab when you come to lab. Being able to tell me the different parts of the cylinder, how to hook it up, the proper steps, like cracking, hooking it up to the nip, whichever one safety system you're using, and how to set your flow. I'm teaching you here about the pneumatically powered machines. And as we continue on with the lecture today, you'll understand maybe a few terms you didn't hear yet, you will hear then, but make sure y'all look at this over the weekend. I have this one from a few terms ago. Then I think I have a couple more in there that was Mr. Boyd last term was teaching about it as well because he did the labs last term. And so as class people, students are in the classroom. And so just watch them, guys. I'm telling you, you need to do that so you're able to understand how to do this so we can get past this unit. This should be your easy 100. So continue to pay attention. We are recording, but you also need to be, if you're live, pay attention. If you have questions, let me know in the chat and I can, you know, go to any kind of questions you might have. But somebody say something in the chat? No. Sometimes the chat be acting up. All right, so here we go. Your tire and you push that little needle and you can hear the pressure come out. Well, that's what these two connections are for, okay? I can hook. I apologize that it's so far away. This was one of my first videos and I had my iPhone kind of backed up a little bit. But I showed you a few of this same stuff on this oxygen cylinder up here. I mean, this air cylinder that I showed you today. It's the same stuff. And I'm not going to expect you to be able to walk in there on Monday and be able to do everything, but it would be nice if I only have to give you minimal instruction. So when you come in Monday with that paperwork, that lab assignment, you must have it complete. You should be able to do this without a problem. I promise you it's easy. Okay, we're going to be in and out, teach you a little bit, make sure you review whatever y'all need, and then you're done. But I'm not going to rush out of there, but I'm trying to make sure you got everything you need to ace this test. I can hook two pneumatically powered machines to these two connections here, all right? Or if I just want to do a nasal cannula, then I can do my nasal cannula or aerosol face mask or anything else like that from this connection, right? That happens from this connection. All right. Now, remember what we said about taking it off. First thing you have to do when you're ready to take off the regulator is to turn the cylinder off, right? All right, step number one to take it off. Turn the cylinder off first. Turn the cylinder off. We turn the cylinder all the way off, and you will notice that there's still pressure inside of the board-on gauge. The regulator is still showing pressure. So how do I get rid of that pressure? I cannot take it off until I get rid of this pressure. We call it bleeding the pressure. We have to bleed the pressure first, right? So what I do is I just turn my leader flow, either turn it all the way up, and you see that? Just went down. Now it is free of that 50 psi, right? It's free. Now I can remove the cylinder, okay? All right, so the first step to take it off is to turn the actual cylinder off. Righty-tighty, turn the tank off. Okay, that stops the flow to the regulator. Now, once I do that, you're gonna have pressure still trapped inside that regulator. And if I try to take the wrench and take it off, it's going in your face, okay? So you have to get rid of that pressure. Bleed the pressure off first by either just turning that leader flow all the way up, like I would this little flow tube there. I'll just turn it all the way up and it will just read the pressure. Or I could push my finger in one of those other ones I was showing you that could hook machines to, push it and it'll out, right? So bleed the pressure off. Now I'm ready to take the regulator off without getting splashed in the face. So I take my special wrench back to the right. Regulator off. Okay? That, guys, is how you start to finish. Put on a regulator to the correct cylinder. Okay? And that will be the big ASSS cylinders. What about the smaller cylinders? It's the pin index safety system. Yes, so here goes the process for the smaller cylinder.
This is a regulator that works off the pin index safety system. If you can see it, it has pins. It has one big place and two small pins there, okay? All right. Remember the position for oxygen, and remember the position for CO2 and the position for air. They all are different, right? So here it is. This is an E cylinder. This is an E cylinder. If you notice, the E cylinder also has on one side 3 pinholes. One big one and 2 small ones. On the other side, it's just a little notch to catch the actual yolk, right? The yolk, all right? So all I do is I line that up. I take the 3 pins on this side, line it up with the 3 pins on my PISS, right? The little pissant tanks, right? The PISS, the smaller cylinders, right? I put this over like this and just work it until it fits right up into the spots, right? 1, 2, 3. Once it fits in there like that, it's snug. I have it flush and it's in there. What I do then is just simply tighten the yoke. Tighten the yoke, right? Now I'm ready to turn on the cylinder. Now, quick question. What didn't I not do before I put on this regulator that I should have? Crucial step.
What did I do? What didn't I do before you put on a regulator? Any cylinder, what's the first thing you should do? Cracking. I didn't do that because what that does is it gets that dust and grime and dirt out of there, because you don't want your patient to be inhaling dirt from because those cylinders are stored outside, guys. You know what I'm saying? They're outside in bulk systems, in cages. Yeah, we keep them outside, okay? So rain, and sometimes they have a little roof on it, okay? But it's still out in the elements. We don't keep the storage inside. Well, we break them from outside and then fill up the rooms, okay? Because on the rooms, we have some empties and we have some fulls. And so it might be your job that day, that shift, to replenish the tanks. So you have this little tank cart that holds about 6 tanks, and you would take that and go pick up the empties, right? And so what we usually do is take that that cart out to the outside with a key. You have a key to a chain, you have to get in. Only respiratory has that key. And we go in and we fill up our little cart with about 6 full E cylinders, okay? 6 to 8, something like 9, might be 3, 6, 9, might be about 9. And then take that, roll it back into. I stop at the one station, like maybe ICU, go to where they store their tanks. I put some full ones in, maybe 3 or 4 full ones, and take 3 or 4 empties, right? Go to the next station and do the same thing. And then I take all my empties back out to the storage place where we store the tanks. And then next air will come. They have a key as well. When they come once a month or once a week, they come and take all of the empties and replenish them with all fulls, right? And then the liquid cylinder that we have, somebody else will come and fill that cylinder up. And it takes about an hour to fill, I think about an hour to fill that big thing up with liquid oxygen, okay? That's the liquid truck, all right? So you got the gaseous cylinder truck that come to the cylinders, and then you have the liquid actual tanker will pull up and back into it and hook to that and fill it up, okay? So that's dust and dirt. And then another thing, guys, it's dust and dirty and rusty because we cannot use oil. You know how putting that helmet, I call it, on there, it's like, oh my God, what is that? But you can't spray WD-40 on there because it's petroleum based, and oxygen supports combustion. So it could possibly flame on you. People who have Vaseline all on their lips, thinking they got pretty lips, right? And they on oxygen, and they just putting their little, oh, you want to put Vaseline on your family member right there on oxygen in the hospital, and the lips get dry and cracky or whatever, and you want to come put a little bit of Vaseline on mama's lips, that could potentially cause a fire, because Vaseline is petroleum jelly, right? That's what it is, petroleum jelly. So it's petroleum based. So it could support combustion, okay? And so that a lot of people smoke while they're on oxygen. And if it so happens to catch one of those cherries, it's going to flame. It flames up in their nose, and it burns their nose, the inside of their nose, the lips be all burnt up because they're smoking on oxygen. On oxygen, but still smoking, okay? And so that's why we have to cracking to blow all that rust and dirt and leaves or whatever else that may have accumulated in the spout. Because if we just take the helmet off and stick my regulator on there and turn it on, it's going to push that dust inside the regulator, which will be inhaled by your patient, okay? So that's the step I missed.
Step that I did not do before I put on the regulator. I'm gonna let you think about it. If you said I didn't crack it, then you would be correct. I did not crack it. Now, I went to get the tank wrench. The cylinder wrench or tank wrench for an E-cylinder looks like this. And this part fits over the top, right? So let me take it back off and correctly crack the cylinder before I put on the regulator. Now let's see. Lefty loosey, righty tighty, always, okay? Always. So I'm gonna put this on here. Turn it to the left, turn this away from you and away from everybody else and say, cracking. See that? That's what you do. Now, we know all the dirt and debris has been removed from the actual orifice. Again, I take the 3 prongs, line them up with the 3 holes on this side, just fit it right down over there and just till I feel it catch and it's flush. It's flush. I take the yoke and tighten it up. Then I cut on my cylinder. Let's cut it on and see if we have a leak. Same thing with the E-cylinder. You will turn it all the way till it stops. And then 1/2 turn back to set it. Okay? Now it's on. Now, when I look at my pressure inside of here, you see that pressure in the bourdon gauge? It's reading about 500. It's almost empty, right? This cylinder is almost empty, okay? That's how we would know. When it gets to about 500, you want to retire that cylinder, put it in the empty, and get you a new one, all right? But we cracked it, we put on our regulator, and we turned it on. This cylinder or E-cylinder would be ready for use. We can plug a nasal cannula up to this one, right? Nasal cannula, small bore tubings, that's the kind of things, low flow systems is usually what we use on the E-cylinders, low flow systems, okay? Now, I'm ready to take it off. So the first thing I have to do is turn the cylinder off, right? So let's turn the cylinder off, righty-tighty. Off, okay? Now, I have to bleed that pressure, right? Because there's still pressure inside of the regulator. So I'll turn the flow meter, right? And it goes down. Now I'm ready to release the regulator, okay? This is how you engage and disengage E-cylinders and H-cylinders, okay? All right. Don't forget, there's also some safe storage or safe handling. This is an H-cylinder. It should always have its lid on it. I told you it sounds real scratchy. Okay. But it's
like, oh my God, I can't deal with that. But no way around it.
And why would not put oil on here to make that less hard to turn or less scratchy? What would be a reason I would not put spray oil on there? Exactly, because it supports combustion. And oil is a product of petroleum, and it's considered flammable. The oil is, okay? But the oxygen cylinder is not flammable, but it supports combustion. All right, so how I stand it up, it's like this, right? This is how it should be stored with a chain around it. Now, when I'm ready to move it, I just have to lean it back, and these wheels pop out, right? There's some wheels that pop out, and it kind of leans to the side. Hold it with two hands, and this is how I would manipulate moving the H cylinder, okay? You'll never go behind you. Always.
No, my bad, y'all. I do what I want to do.
I'm ready to move it. I just have to lean it back.
Spring.
And these wheels pop out, right? There's some wheels that pop out, and it kind of leans to the side. Hold it with two hands, and this is how I would manipulate moving the H cylinder, okay? You'll never go behind you. Always keep it in front of you so you can see what's going on, okay? This is the safe way to move or manipulate the H cylinder, all right? And when I'm done manipulating it, I take it to where I'm gonna put it and stand it up. All done. The E tank or the E cylinder is always on these little crop stands, right? It's just a stand with two wheels, and you keep it in there, and this is how you move it around, okay? You can roll this one around like so, okay? That, you guys, is basically the cylinder lab, okay? That's the lab. So look at this video, watch me put it on and off, talk about the different components, and be ready to check off when, if we ever get a chance to come back together and do this. If not,
that was when the coronavirus had hit. There was nobody on campus. I was just up here recording labs, trying to have them prepared so that, you know, students have a chance to look at some stuff before they come in. Okay, so can you see my screen right now? Moving around. Okay, so this is the module, guys. You got the cylinder lab I just showed you, right? Mr. Boyd's instruction there, and then the lab instruction there. You know, it's going to also help you if you want to look at those too. Look at those over the weekend. The gas laws video, I hope you guys looked at that because I showed you that yesterday. Or well, I didn't show it, but I told you to watch it, right? The gas laws video. All right. This is the live lecture right here. It was at the bottom. You might not have saw it, but I hope you saw it because it's right. It was in there. All right. Set that into an indent. Okay. Live lecture from yesterday. You're going to watch the lecture for today. So let's finish up the let's go ahead and finish up the actual lesson plan. All right. All right, so that just showed you those proper on and proper off to turn on or to activate or deactivate a cylinder. All right. Store with the cap on, of course, to prevent breaking that stem. Cylinder testing. We said we do hydrostatic testing every 5 to 10 years. Need to know that. And it's done by water displacement, right? So they put it in the water, fill it up, and if the water moves, that means that the actual cylinder is out of round, right? It's weak in a weak spot somewhere, all right? This is a little diagram here of just a basic, looks like an H cylinder, has the hand wheel turning on and off, the oxygen outlet here, the valve. Some of them have a little pressure safety device there, some of them don't. But like on the back right here, it shows how it's got the hydrostatic testing date stamp seal on there for the original, right, when it was done. On the other side is what it is, oxygen and the DOT and all those things that are on the front and the back of the cylinder. Don't forget that. Now, gaseous bulk system. We got a couple types of bulk system. We have the standard bulk system, which is the large H or K size cylinders banked into a manifold system. These are just some big, large cylinders. This one says flammable, so you know it's not oxygen. I don't know what it is, but I've just showed a few pictures of how some gases are stored on properties. You also have a primary bank. So that standard one has a primary bank and a reserve bank. Basically, that's just saying you have some large cylinders manifolded together. You have a primary bank of them and you have a reserve bank. When that primary bank gets to a certain level, then the reserve will kick on and a message will be sent to the company who fills them to come fill up your primary bank, okay? The hospital can never be without oxygen, okay? It has to make sure that it always has an ample supply. I think it's at least 24 hours of reserve oxygen, okay, to give the company time to come and refill, right? Fixed cylinders. This is an example of a fixed cylinder right here, okay? I think this is argon and oxygen mixed for welding, right? This is a welding company here that have a large fixed cylinder. See how large that is? Some of them have a large bank of 75 of them. It could just be one big one, okay? But it's just letting you know it's refilled on site by the liquid O2 truck that converts the liquid into gas to fill the tanks, all right? So when you have a large oxygen or liquid oxygen cylinder, that's how we store it. So we said it makes more economical sense. But what happens is it's pipes. It has pipes that lead away from that. And as it leads away, it heats up, right? And rises above critical temperature, in which the liquid can no longer remain a liquid and turns into a gas, okay? And then that gas is pushed into the hospital. And I have a great picture of oxygen piping systems inside an actual hospital. Then you have trailer units. These will be actual units of oxygen on the back of a trailer, like a truck. That's usually for when they're having some kind of construction, right? And they need oxygen or nitrogen or something for welding, and they'll have it on a truck. And so they'll come and drop the trailer off, and you use it. When it get low, they'll come drop another one up and pick that one up with the truck, okay? Like, you know, the 18-wheeler. And it's the same looking one that comes to fill the actual standard big liquid tanks. Sometimes they have them, they just bring the whole truck and just drop the unit off, come back and get it when it's running low, all right? Very large cylinders mounted on trailers, towed to a central location for connection. When it's low or in need of maintenance, it's replaced with a fresh trailer, okay? Now, liquid O2, remember, liquid now, the critical temperature is -118 or -181, all right? But it's stored colder than that, because what sense would it make to say, all right, don't let this chicken get below or get above 20 degrees Fahrenheit. Would you store it in the refrigerator at 19? No, you're gonna store it good and below 20, so it has no chance of going bad, right? Well, the liquid critical temperature you learned was what? -118 and -181. Either one is Celsius and one is Fahrenheit, okay? Above that critical temperature, it cannot remain a liquid. So we store it at -183 Celsius or -297 Fahrenheit in a thermos bottle type store, just like a thermos. The cylinder is like a, you know how a thermos is insulated, okay? To keep it cold. Inner and outer steel shells separated by a vacuum. That keeps it good and cold. So that way, if we store it that way, we don't run a risk of it turning into gas on us, okay? So what is the critical temperature exactly? Negative. You got to say negative, because you will have a choice in there that says 118. It's -118 or -181, okay? Which one is which? I mean, tell me to me. Negative. Celsius, okay. Good. All right. That's the critical temperature, but that's not it where it's stored at. So if you get a question that says liquid oxygen is stored at, and then they have the critical temperature on there, you're going to be wrong. We don't store it at the critical temperature. We're going to store it much colder so it doesn't have a chance of turning into vapor on us, okay? Now, it's a little bit different with the pressure reading. Pressure readings do not indicate the remaining of oxygen in liquid, all right? The pressure tells us how much oxygen is left in a gaseous cylinder, right? So let's look at it. This is a board-on gauge here, okay? Up close where you can see it better. When I hook up, and this is the nipple and threaded nut, so this is the ASSS, right? I will hook this to my cylinder, and when I turn my cylinder up, this board-on gauge will read how much pressure is in the unit. And you see about 2200 is considered full. See that green full? All right? In that range, that's considered full, okay? And so that tells us how much oxygen is left in a gaseous cylinder, all right? And this one over here is simply the liter flow. So once I turn, this is all together. When I put this on, I can turn this part to determine my liters per minute on this side, okay? But the pressure, which is the board-on gauge, this is a board-on gauge meter, and that tells us how much oxygen is left in a gaseous cylinder, right? But the liquid O2 is different, okay? The liquid O2 is different. The pressure does not tell us how much is left in liquid. We simply have to weigh it, okay? Pressure readings do not indicate the remainder of O2 in a liquid system, okay? Because liquid oxygen does not exert a gas pressure. So how do we know how much is left, Mr. McCarthy, in a liquid system? We have to weigh it. You know? Oh, okay. We have to weigh it. The weight will indicate how much O2 is left in a liquid system. Okay? You just weigh it. Now, look at this. The pressure inside of a liquid oxygen tank doesn't even exceed 250 psi in the container that it's holding in, right? So that, you know, that's wonderful. We can get way more oxygen out of a liquid. It doesn't have a whole lot of pressure. You don't have to be threatened by if it cracks, it's going to blow up and fly across the city, right? It's much safer and it's more economical to use liquid as opposed to gaseous, all right? So how do I know how much oxygen is left in a liquid tank? By weighing it. Okay, by weighing it. Okay, by weighing it. All right. Piping systems. Now here we're getting a little bit more liquid oxygen systems going into these pipes. See this? You got the liquid fixed cylinders. The truck will come, next air, whoever will come and hook up to them and fill them up with some cold liquid oxygen. And that liquid oxygen will go through these pipes. You see these little pipes? And they go through these columns, which warm it up a little bit and turn it into gas. That gas is then piped into the building, okay? Piped into the building. So you have piping systems, and they have zone valves in the hospital. Now, you'll notice at different nurses' stations, there'll be a little box in the wall, not a fire hydrant, a fire extinguisher, but another little box that has 3 pipes. It'll be the oxygen pipe, the medical air pipe, and the suction or vacuum pipe, okay? It's those 3. And if something happens, if there's a fire in a certain part of the hospital, the fire chief will tell the respiratory therapist, please cut off the oxygen to zone 10 or whatever. And you'll learn those zones once you become employed, okay? And so you have to go to that zone, open up that glass, and turn off the oxygen. It's gonna be just a little like a valve that you turn on and off, okay? And you turn off at the piping at the zone valves. There's different zones. You got zone 1, zone 2, whatever in the hospital. And if there's a fire in zone 1, you want to get to zone 1 and turn the oxygen off because oxygen supports combustion, right? So if fire gets into that line, it's going to explode, all right? You don't mess with that unless told by the fire chief, all right? Now, still talking about liquid. Liquid oxygen is most economical. Now, we talked about the cubic feet of gases. Look at this. 1 cubic foot of liquid is equal to 860 cubic feet of gaseous O2 at regular room temperature. Okay? That's amazing. 1 cubic foot of liquid can give me the same amount of work as 860 cubic feet of gaseous. That's why we use that. That's why we store it in liquid. If we stored it in gas outside, it would be huge tanks. It had to be about 300 huge tanks on the property, right? It's like, what is all of that? But now we don't need but 1 or 2 because of the economical part of it, okay? It's so much better to use liquid than it is to use gaseous as far as storing is concerned. Liquid O2 cylinders are used when there are when usage is too large for cylinders and not enough for a permanently installed liquid vessel. All right. Then we have what's called fixed station. Those are stand tanks. Large spherical containers with gaseous equivalents to 130,000 cubic feet refilled by service tank trucks. Equivalent, right? So we have some large, and this is all talking about the same stuff, guys. You don't have to remember every little part of this different stuff, okay? But just know that liquid is most economical. We use that by storing that outside the hospital, right? We weigh liquid oxygen to tell how much is left. We don't do the pressure. Pressure is only for the gaseous cylinders, all right? And you use the duration of flow formula to find out how much time you have on a gaseous cylinder, all right? But for liquid, you have to wait, and there's a formula for that as well to tell how long it's going to last. You're going to learn that in a minute. But just know that there's several different types of ways we can store bulk oxygen, okay? In the trailer units, standalones, bulk systems together, right? Manifold systems, all of that stuff, okay? Bottom line is what I just told you. Make sure you understand that key points, okay? Those key points. It's just the simple stuff, all right? This is the picture I was showing you. This right here, guys, will be liquid O2. This is the liquid O2 tank, right, or cylinder, that fixed cylinder, spherical cylinder. This is the truck, Praxar or NextAir or whoever will come and fill this up with liquid oxygen, okay? That liquid oxygen will then travel up and down these coils. I don't know what they're exactly called, but they travel up and down these coils. As they do that, they warm up. They go above critical temperature, right? And turn into gas. Then you have some gas being stored in here. This will probably be, no, I'm sorry. This will probably be like a secondary little liquid right here, just in case this one starts running out or whatever. But this then, guys, look, is pumped into the hospital. You're pumped into this room, right? Into this room. It's pumped into these rooms, these medical rooms here, patient rooms, different, like a little doctor's office where procedures might be happening, like PFTs, right? When we do PFTs, we have a desk, computer. You're in your lab coat. You look nice, right? You got nice pictures on the wall. It's not a hospital room. It's your office. But you have a body box in there for their pulmonary function test. And you got to have gas. You got to have oxygen. You got to have medical air to do your test. So it would be pumped in this room. Look down here. This is the storage room, right? This is where respiratory will come and store, pick up empties and fulls and take them around to have little extra tanks in each one of these rooms, okay? And then you have where maintenance will be down here, making sure that the piping systems are working, right? It's not respiratory. This will be the maintenance guy. This guy here will be, or a gal, whoever, will be down here making sure that the stuff is pumped in like it's supposed to and going throughout the hospital, okay? This is their liquid O2 or oxygen piping systems into the hospital, okay? Into the hospital. Amazing how it works. All right. All liquid O2 tank containers are equipped with 50 PSI reducing valves. Remember that. The standard working pressure of oxygen after it leaves the system, it's down to 50 PSI. The standard working pressure of oxygen is 50 PSI. I can't use this oxygen cylinder at 2200 PSI and then hook it right to your nose, right? I'm gonna blow your head off, okay? I have to reduce that pressure to a working pressure where I can use a system or use a machine, put it on a nasal cannula or whatever to get it to my patient, right? To use the DISS, I got to get that down. I can't put 20,000 or 2,000 in a DISS. It's got to be worked down. And these regulators work them down, right? These regulators will reduce the pressure in the cylinder or in the wall to 50 PSI. This is a regulator, and it will reduce the pressure from the cylinder, the E cylinder, because this goes on the E cylinder, because this is the PISS, right? Pin index safety system is on E cylinders and smaller, all right? The little pissant tanks. But it's still 2,200 PSI in that little tank, right? And so therefore I have to reduce that pressure down to 50 PSI with a regulator. This regulator has a gauge on it called the Bourdon gauge. See that little, if it's in the red, it'll let you know, hey, you need to refill that system, okay? Once I turn on the system, it's going to pop up to 2,200 if it's full, right? But if it's not, you just read wherever it is and tell Mr. Johnson how long he has, right? Once I turn it on, I can control the liters per minute right here. The doctor says, I want him on 2 liters. Well, I turn this to 2 liters. Okay, 2 liters will be coming out of here to his little nasal cannula, and that's what he's on. Okay, if he's on 3 liters, we go to 3, 4, 5, 6, 8, 10. It just jumped to 12. Okay, this one goes up to 12. All right, or you can even do a half a liter, right? 1 liter. Just depends on how much they need. All right, you're always going to use just enough oxygen to overcome hypoxemia. Right? If 2 liters is enough, use 2. You don't got to use 5 liters if 2 would have did it. All right? So this is a regulator that brings that working pressure down to 50 PSI. Same thing with the ASSS, right? It's going to hook up to the larger cylinders, right? And it's going to also bring the pressure down to 50 PSI, so I can use it right here. It'll be 50 PSI coming from here, okay? And I turn this part, and this will control my liter flow. All right, several different types. This is one type of ASS. The one I showed you earlier, that's another type, right? There's several types of ASS regulators, all right? But when it gets down to, go too fast. So let me go back. All right, we're almost done. Now, how long will the liquid last? All right, it's simple. It's pounds of liquid times 344 divided by liters per minute. All right, it's the pounds of liquid times 344 divided by liters per minute. Okay, so you just work it out like you would work out the other one, guys. The same thing about reducing to the lowest hour, you know, the same thing. All right, so for instance, I'll just say one, you tell me. Mr. Johnson has 30 pounds of liquid oxygen left in his tank, and he's on 2 liters per minute. How long will his oxygen last? Again, he has 30 pounds left in his liquid system, and he's on 2 liters per minute. How long will his system last?
Can you say that again?
He has 30 pounds left in his liquid O2 system, and he's on 2 liters per minute. How long would it last? 30 pounds left in his liquid O2 system, and it's running at 2 liters per minute. How long does he have before it needs to be refilled? Yeah, they're always going to be in minutes. Yeah, liters per minute. Mm-hmm. So how much time does he have? You're going to see how much farther this goes than gaseous. That's why a lot of people use liquid O2 at home now. They use little liquid units. Okay. like a little thermos in a bag with a nasal cannula hooked up to it. Lasts so much better. How long will it last? No, 30 pounds of liquid. He has 30 pounds left. It's 30 pounds. It's from pounds of liquid times 344 divided by the liters per minute. He's on 2 liters per minute. Good, Kayla. Good, Miss Thomas. What you looking like, Miss Rose? No, it's longer than that. So, oh yeah, 86 minutes. do 30 times 344. What you get? Huh? You did 30 times 344. Okay, 30 times 344, 10320, right? Now that's divide that by 2. What you get? Minutes. 5,160 minutes. Now divide that by 60 to get how many hours? 86 hours. Okay, and then divide that by 24 because you don't want to tell me you got 86 hours. Divide that by 24. How many days you got? About 3. 3 days on that oxygen. If he's got 30 pounds left, he at 2 liters per minute, then he has about 3 days left. Okay, see how much better that is? Much better, much more economical. Okay, that's how you do duration of flow for a liquid system. Okay, liquid. Now, safety precautions. Must have a 24-hour reserve or backup supply. Hospital must have 24 hours. If something happened, power go down, you have to have at least 24 hours of oxygen left. And the hospital must have a procedure for total system failure. What if the power don't go out? It's just the whole bulk system just malfunctions. They have to have a backup plan, some type of procedure, somebody they can call to help them get there like that, okay? Or telling everybody, okay, now you need to go to the bottom and I need all hands on deck to go get how many H cylinders we can get to the units, right? So we can plug up ventilators. So people are on life support. And if everything go out, they're not getting any oxygen. Now you got to hook that machine up to the tank. So every ventilator gonna have to have its own oxygen cylinder, okay? And that could be a lot depending on how many beds you have, all right? So that could be a disaster, but you gotta maintain. All right, now we're gonna talk about the concentrators. These are little machines that make oxygen, okay? You might have seen this in somebody's house before or know somebody in your family that has it. This is an oxygen concentrator. What it does is it pulls in outside air and scrubs it in different ways and produces pure oxygen, okay? It runs 24 hours a day, 7 days a week, as long as you have power, okay? So Mr. Johnson, who's on 2 liters per minute, 24 hours a day, he'll be on this concentrator while he's at home, okay? He'll have his little concentrator, watching the game, cooking dinner, whatever, sleep, whatever. But if the power go out, he needs to hook to his 8 E-tanks, right? He got to hook to his E-tanks, or some of them will have an 8-cylinder in a closet somewhere. And all else fails and my E-tanks go low, I got to hook up to my 8-cylinder until the fire department can get there and give me oxygen, or the DME, which is the home health company, the home health respiratory therapist who's on call. So Mr. Johnson called Miss Rose. He's in Corinth, Mississippi. His power is out and his concentrator is not working. If you happen to be the therapist on call that day, then you got to get up and take him some oxygen. So you'll go home with your van, right? You'll have the van with stocked up with your oxygen cylinders, your concentrators, whatever. If his concentrator just don't work no more, you switch it out, okay? And so he'll call you at 3 o'clock in the morning and say, or he'll call the hospital, the company, and the answering service will page you, right? The answering service, the patient don't call you. The answering service will call you and say, hey, I got a patient in Mr. Jones in Corinth, Mississippi. His concentrator is malfunctioned. He's on his E-tanks now. He needs you to come out. And so you say, okay, you get up, clock your time. As soon as you get that call, you own clock, okay? You own the clock till you get the call, get dressed, go drive all the way where you're going, fix the problem until you get back home, then you off the clock again. So when you on call, you get paid for being on call and on top of the time you took to go out. You get your pay rate for when you was activated, okay? Usually DME companies, you have about 3 or 4 therapists, so y'all rotate call. You'll be on call for a week, then somebody else on call for a week, then the third person on for a week, then it's your turn again, okay? I did that for about a year or two. It was cool at first, but I just didn't like, it's not for me to be getting up, going and doing all that. Some people love it, you know, some people love it. You can kind of get up and be at your own leisure. You got little tickets where you go out and set up oxygen setups at home, work on people's CPAP. If they have a problem, go out there and switch it out, little stuff like that. If that's for you, that's for you, okay? But being on call, I mean, it was cool because I used to like driving that nice little size truck out and during the day, but being on call, I didn't really like it, okay? But you got 2 types of concentrators. You got the membrane type. So make sure you highlight that. You have the membrane type concentrator, right? And you have the molecular sieve. 2 types of concentrators, the membrane type and the molecular sieve. The membrane is a little 1 micron thick membrane, and oxygen and water pass through it, the membrane, okay? Now, oxygen and water pass through faster than the nitrogen, because remember, nitrogen is 78% of the outside air. But when it's sucked into the concentrator, the water and the oxygen from the air go through the membrane and the nitrogen really doesn't, okay? And so what happens is that oxygen that came through it scrubbed the nitrogen out of it and gave you just the oxygen, right? And so it's able to give up a FiO2 of about 40%. Okay, you can get up to 40% oxygen on the membrane type, okay? Then you have a little bit better one called the molecular sieve type. And what this is, it has a little sieve bed that's filled with sodium aluminum silicate, little pellets, little sodium aluminum pellets, right? Air is forced through those pellets, and those pellets scrub all the nitrogen from the air and can deliver up to 90% oxygen at 2 liters to the patient, okay? And so it says the higher the flow, of course, the FiO2 decreases. You're going to learn why when we get to the next section, okay? So the membrane type and the molecular sieve. So you need to know how the membrane type works and how the sieve works and about the FiO2s that each one can deliver. Now, the regulators and the flow meters, here they are right here. You have a regulator, which I showed you already, which reduces the standard working pressure down to what? What's the standard working pressure? 50 PSI. Then you have your flow meter that controls the flow, okay? And so it just depends. Some regulators have a flow meter built on, right? This was your flow meter, right? Remember I told you could turn the liters per minute on with the flow meter. This is the regulator, but this is the flow meter part right here, all right? Or you can have a wall unit that's already your regulator, right? The wall unit breaks down from the pipes down to 50 PSI and looks like this. And this will be either screwed into the wall, right? Or pushed in, depending on what the hookup that they have. But this is the flow meter. See, I can turn this right here and the little, see that little ball in there? That little float, that's called the float, right? The float will determine how many liters per minute I'm dealing with. And this happens to be a large one that has up to 60 liters per minute, right? So they're made a little bit bigger. You see, you got 10, 20, 30, 40, 50, 60, like that. But this is your flow meter, okay? This is called a Thorpe Tube. This is a flow meter that is called a Thorpe Tube, okay? Green means it hooks up to what? Oxygen. The yellow one would hook up to yellow. The yellow Thorpe tube only hooks to
Medical air.
medical air, right? Medical air. Just like the yellow one that's on this one, right? You have a yellow flow meter on the yellow cylinder, okay, for medical air, okay? Now, so these are the flow meters. You have Thorpe Tube flow meters and you have regulators, okay? Now, what did I tell you this gauge? What this gauge called? Bourdon gauge. Good. This is the Bourdon gauge that's built into this regulator. And this regulator will bring the standard working pressure from 2200 PSI down to 50 PSI, okay? Once you do that, you now can control the flow meter right here, or if you have one of these, the 50 PSI has already been reduced in the wall of the hospital. And you would screw this up to it, and this will be controlling your flow to your patient. He'll hook up to here. This is a little extension we call a Christmas tree, right? This is the DISS part, but you can't really get some nasal cannulas are too small to put here, so we use this little adapter, right? This is an adapter, O2 adapter. Some people call it a Christmas tree, and you put the Christmas tree on there like that, screw it on there so you can push your little tubing on there for your mask or your nasal cannula, okay?
Would those be used more in ICU patients?
What?
Or is that the one you just had in your hand?
Yeah, this is in all hospital rooms, just regular rooms or ICU. This will be in there. You use this more for people that's going home or traveling, right? If I got to take Mr. Johnson to X-ray from his room and he's on oxygen, well, I can't take the wall with me, right? I have to take a tank. I put the tank on the side of his bed and hook this one of these up to his tank and put him on his 2 liters while he's on his little trip to X-ray or MRI, or wherever he got to go, okay? And then when he get back, I turn this off and put him back on the wall, okay? Now, but this one here, this type of flow meter is in every single patient room at the hospital, okay? Every single patient room. And for the patients who are on ventilators, you still have one of these on the wall, but you also have the spigot coming out of the wall as well. So I can take this off the spigot and screw my machine straight to the wall. All right, I can't do that, which I can show you that when you come to lab. It's the same wall unit. It's either I'm using a flow meter or I'm straight up just gonna screw my machine into it, my life support machine, which is the ventilator. I wouldn't really want to put that on a flow meter. I would take the flow meter off the wall and screw my oxygen line from my machine straight into the wall, and then take the air line and screw it into the air part of the wall, okay? Because you need both oxygen and air to run your machine, okay? So that's how we do that. Now, there are some specific things you need to know about regulators and flow meters that we're gonna learn now. All right, but good question, Kayla, good question. All right, so your regulators reduce high pressure down to 50 PSI. Now, it can do it either in one stage or multi-stages, all right? A single stage regulator will reduce the working pressure in one step, okay? And that means it has one pressure relief valve there. If it does it in 2 steps, it has 2 pressure relief valves. If it does it in 3 steps, it has what? 3 pressure relief valves, okay? You count the valves to tell you how many stages that regulator is. So if it has 5 pressure relief valves, then it's a 5-stage regulator. If it only has 1 pressure relief valve, it's a single stage regulator. But they don't usually say 2, 3, 4, 5. They just say either single or multi, okay? It's either single staged or multi-staged, okay? So look right here on the wall. This is how the wall units look, right? You got oxygen and you have medical air. You can just unscrew, like I just showed you, just unscrew this one and plug your ventilator right into the wall if you need to, okay? But at the wall right here, it's already down to 50 PSI, okay? The wall has already brought it down. This little gadget in the wall, which is a regulator, wall unit regulator, it has brought the pressure from the pipes behind it down to 50 PSI to be used, okay? You got an air one and you have an oxygen one, okay? And to know how many stages that regulator takes to bring it down is by counting the pressure relief valves. If it only has 1 pressure relief valve, it's a single stage regulator, okay? Single stage regulator has 1 pressure relief valve. If it's a multi-stage regulator, it has more than one pressure relief valve. Okay? You good?
Okay, so we're talking about the regulators that you're showing.
This regulator, yeah.
Okay.
This regulator. This is a regulator. This is a flow meter. This is not a regulator. This is a flow meter. Can you see me on the screen too?
Yeah.
Okay. This is a regulator. I mean, this is a flow meter. I'm sorry. This is a flow meter called the Thorpe Tube. Okay. This is a regulator. All right. This is a regulator. Now, the wall is, you can say the wall is a regulator as well. Okay. Because it's built into the wall. But if I'm looking at these regulators and I want to know, hey, is this a single stage or a multi-stage? Well, I can't really look at it I have to be able to know which one it is. It's going to have to be either written on here or something like that, okay? But by knowing, if I could see through here, I could count the pressure relief valves. If it's more than one pressure relief valve inside of here, it's a multi-stage regulator because it takes more than one step to get it down to 50, right? It may come from 2,200 to 1,000 and then down to 500, then to 50. You know what I'm saying? It just depends on how many times it takes it to get it down. That's the stages that it is, okay? Don't make it hard. If it's one pressure relief valve, it's called a what? Single stage regulator, okay? It does the job in one step, right? Does the job in one step. And that's usually what we like, right? When we want something else, I want a medicine that's gonna do the job in one pill, right? I don't want to take 5 different blood pressure medicines, right? Give me them in one pill. If you can make that happen in one, that's better, right? Then say, okay, I got to take this one at 9, take this one at 10, take this one at 11. Now I'm good, right? That's too much, right? I want one step. That's the best kind, all right? So a single stage regulator does the job in one step. And the job is getting down to what? 50 PSI. That's the job we're looking for. This is a couple of pictures of some regulators here. This is a regulator here for an air system. Looks a little different, right? This is also a regulator. This one is called the pulse dose. This is cool because you hook this one up close. This is still the pin index, right? You see the little yoke and pin with the board-on gauge right here. But the good part about this one is this one only gives oxygen when the patient breathes. So instead of it continuously running, it's in the nose, but it doesn't give a burst until you breathe. So when the patient inhales, it gives a pulse dose of 2 liters or 3 liters, whatever they own. If they're on 3 liters per minute, it will shoot 3 liters for every time they inhale. And that's good because you're not wasting oxygen, right? It's going to last a lot longer because it's not continuously running, okay? But this one over here is the standard one I just showed you. This just happens to be silver, but this is just like the one I just showed you. Okay, yoke and pin, that's the yoke there, and it's a pin going into your E cylinder and your board-on gauge. All right, the multi-stage regulator reduces tank pressure to working pressure in 2 or more steps, okay? And it's gonna have more than one pressure relief valve, all right? The more stages, the less fluctuation of working pressure. See, if you got one stage, they say sometimes it can fluctuate. And if you have more stages, then you have less fluctuation. But you don't have to remember that part. Just know that a multi-stage regulator, guys, has more than one pressure relief valve, okay? It does the step in more than one step. 2 or more steps is a multi-stage regulator, okay? You got that, Kayla? Ms.
Yes,
Thomas,
sir.
Ms. Thomas, you good?
Yes.
All right. But I think that's all we got. Yeah. Preset regulator. A preset regulator is single or multi-stage regulator that is set to have pressure reduced to a standard working of usually 50, so it's preset. Now, standard working pressure, guys, is 50 PSI, but there are some that want more than that. So I can get a preset regulator to say, okay, I want you to be 55 PSI, or I want you to be 40 PSI, or I want you to be 60 PSI, right? That's not standard working pressure, but I can preset it to whatever pressure I want it to be, all right? So that's a preset, and that can be single or multi-stage. It don't matter how long it takes to do it. I want you to be 60, not 50, right? So I would have to get a preset one that's already set for just that one, all right? So this one right here, this is considered, not only is it a single stage, but it's considered preset, because this one gonna bring it down to 50, and that's it, okay? This brings the standard working pressure down to 50 PSI. Now I can buy one that's adjustable. Look at the next one. The adjustable regulator, I can change the working pressure, okay? Today I got it on 50, but there might be another machine that takes a little bit more, right? Well, let me put that to 100 PSI for working pressure, right? That's all that is. It's just saying you got adjustables, preset, or single or multi-stage, okay? So let's go back. Regulators reduce the high tank pressure to 50, usually 50 PSI. That's why it says usually, because some of them are preset at different pressures, right? But usually about 50 PSI. You have it, you can do it in one stage, which is a single stage regulator, or it can do it in multi-stages, which is more than two. I mean, two or more, right? Two or more pressure relief valves inside of here means it's a multi-stage regulator, okay? Then we said the multi-stage regulator will reduce that tank pressure to a working pressure in two or more steps, all right? Each stage has a pressure relief valve. So if it's a multi-stage, let's say if it has 3 pressure relief valves, then it does the job in how many stages? 3. If it has 5 pressure relief valves, it does the job in how many stages? 5, okay? If it has 1 pressure relief valve, it does the job in 1 stage, all right? Talked about the preset and adjustable. Adjustable means it can be single or multi, but it can be adjusted, right? It can be adjusted. Now, I've never seen an adjustable regulator, and I really don't know. You really won't know if it's a multi or a single stage without knowing for sure, unless it's written. I don't think it's written on here anywhere, right? So I really don't know how you can tell other than knowing what's inside, right? If you could see through it, then that's how you would tell, all right? Otherwise, it'd have to be written on there. Now, very, very important highlighting information for the Thorpe Tube. This is a flow meter called the Thorpe Tube. It's a vertical funnel-shaped tube with a float. That little ball in there is called a float, okay? So the way you see it on the screen right now is just like this. You got the gas pressure coming in, and you have the float, and you have your there's a needle valve inside of here, and then you have your adjustable knob, okay? Just like this. Gas goes in like this, goes in like this, goes in like this, okay? Now, the Thorpe Tube can be either compensated or not compensated, and we want compensated, okay? If it is compensated, then if I was to put my thumb right here, the ball would drop to 0. That's good, because what if Mr. Johnson is his bed or his wheel of his wheelchair is on his nasal cannula, right? So if we have a nasal cannula here, I went and got a nasal cannula, and Mr. Johnson is on his nasal cannula, right? He got his nasal cannula. I'll put it on. It goes like this, and behind the ears. I have to adjust a little bit more. Like this, behind the ears, and then you snug it up on the neck, just like that, okay? And I will have this hooked to his flow meter, like this, okay? While it's on, the ball or the float, say I got it on 2 liters, right? The ball will be sitting right at 2. And I'm watching the game, having a good time. But then I roll to get some more chips, right? And I roll, my wheelchair rolls over part of the tubing, and it becomes kinked, right? If there's a kink in the tube, then I'm not getting oxygen no more. If the Thorpe Tube is compensated, then that ball is going to drop. Saying, hey, he ain't getting no oxygen, right? You see that, say, damn, what? I know you on, what's going on? Then I start searching from here to him. Oh, there's a kink. And what I would probably know is, you know, he's watching the game in his hospital bed, and his arm, you know how the bed has rail, the bed rail, if you put it down and it pinches that and kinks it, well, then his oxygen on the wall gonna start dropping, right? He got 90%, 89%, 88%, beep, 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 beep. And I'm like, well, what's wrong? What's going on? I see his oxygen. I'm gonna check his probe. Is it your probe or what? Then I say, oh, it's kinked, right? Because I looked up here and the ball is saying 0, right? So it's kinked. That's a compensated Thorpe tube. If it's uncompensated, guess what? It's gonna stay at 2. Even if I kink this, it's still gonna read 2 liters on the flow meter, even though I'm not getting anything, because it's not compensated. And that's not what we want. We don't like the ones that are not compensated, because if my patient nasal cannula becomes kinked, he's not getting his oxygen, but the flow meter will say, yeah, he's getting it. And so then we're gonna be thinking something else. We may do more drastic measures that don't even need to be done, right? We might say, oh my God, let's go put another mask on. What's going on, right? In panic, when all you needed to do was say, hey, it's okay. It's just because his Thorpe tube is not compensated, right? So that's what you want. You want the compensated one, because if it becomes kinked or blocked, or what if he has a bunch of boogers right here, right? What if there's a bunch of boogers in this part? It's gonna block the flow, right? It's gonna block the flow, and if it's blocking the flow, then it's gonna drop. The ball gonna start dropping and say, hey, he's not getting that 2 liters that you said he's supposed to be getting, okay? So how do we know if one is compensated or not? There's something that you gotta know, and it's about the needle valve. Everybody say needle valve. Needle valve. All right, let's find out about this mysterious needle valve. Here it is right here. Compensated Thorpe tube flow meter has the needle valve is distal to the float. What's distal mean?
Farthest away.
Farther away, away from, distal, right? Distal is away from or after, right? So look right here. Here's the ball, and this is the needle valve, right? This is the needle valve, and this is the ball, the float, right? What does it say? The needle valve adjustment is distal to the float, right? You see that? It's after. If I'm coming from left to right, I'm looking at the gas coming from the wall right here. So from left to right, which one comes first, the ball or the float? I mean, the float or the needle valve? The float. So in this case, the needle valve is distal to the float. So that is a compensated flow meter. That's what we want. If this needle valve was before the float, it would not be compensated. Okay? If the needle valve was over here, it would be proximal to the float, and that would be uncompensated, right? So it's very important. The compensated Thorpe tube, the needle valve is distal to the float, period. All right, so I'm gonna ask you a couple of questions. I want you to tell me compensated or not compensated because of some terminology that you learned in 210A, okay? That's why you have to go back and look at your terms, all right? Now, tell me true or false. In a compensated flow meter, the needle valve is distal to the flow. True or false? True. Okay, everybody got that? Everybody got that? Okay.
Yes.
Next question. True or false? In a compensated flow meter, the float is proximal to the needle valve. True. True. The float is proximal, which means it's before the needle valve. Okay? So that's how you got to do it, because the test question is going to ask you stuff like that. It's going to be like the need it might be like a multiple. In a compensated flow meter, the float is proximal to the needle valve. That's correct. Just like if you said the needle valve was distal to the float. That's also correct. But what if I said in a compensated flow meter, the float is distal to the needle valve? Would that be true or false? False. okay? So you got to know your directional terms, all right? Make sure you know your directional terms. Now, and that's hard as it gets, guys. That's hard as it gets. There's not anything else about the Thorpe tube that's very, very, very important other than compensated or not, okay? If it's compensated, then this needle valve will be distal to the float, right? If it's compensated, the float will be proximal to the needle valve. Now, you don't see the needle valve. You don't know where the needle valve is. It's going to have to say it on the Thorpe tube, all right, whether it's compensated or not. They're just telling you how they're made if they're compensated or not, okay? So what happens is the indicated flow is accurate in the presence of back pressure. So if there's back pressure, the indicated flow is going to drop. So it's accurate because you're supposed to be on 2 liters, but now he's on 0 liters because I got it blocked. So the float should read 0. It should be accurate, right? Then when I release that kink, it should go back to where it was set, okay? In an uncompensated flow meter and I kink the tubing, it's going to stay at 2, all right? It's going to stay at 2. Now, to check for compensation, it's either labeled, sometimes it's labeled, you know, it's going to say compensated. So let's look at this one, see if I can find whether this one is compensated or not. All right, let me a minute. 50 PSI, oh, there it is right there. So let me see. You see how it says labeled calibrated at 70 degrees Fahrenheit, 50 PSI, or if you have a visualized needle placement, some of them you can see, okay? But look at this one. I'm gonna turn the camera where you can see it. Tell me, do you see any of that right there? You see that calibrated at 70 degrees Fahrenheit? See it?
Yes.
See it, Ms. Rose? Okay, because you can't hardly see. All right. Calibrated at 70 degrees Fahrenheit, right? And also says 50 PSI right there. You see that? So that lets you know this is a compensated Thorpe tube. All right, it's compensated. Another thing would be, and which I can show you more when we get to lab, if I was to plug it up to the wall, as soon as I push it in the wall, the ball will go up and shoot back down. That's another visual sign that it is compensated. If I push it into the wall and that ball don't move, it's not compensated, okay? So how do I know if it's compensated? First of all, the needle valve is distal to the float, or the float is proximal to the needle valve. Don't let that trip you up, okay? It also will either be labeled at 70 degrees Fahrenheit, 50 PSI, or visualized needle placement if you have one that you can see the needle valve. This one you can't, all right? Also, you can turn the unit off and plug it into the wall and it will rise and fall. So that means after you turn the flow down to 0, right? As soon as you turn it all the way off, this is turning it off, righty tighty, lefty loosey. Turning it on. So it even tells you on and off. Can y'all see that? Okay, on and off. Once you turn it all the way off, take it off the wall. Screw it onto the wall and that ball jumps up and goes back down, it's compensated. If the ball don't move, it's not. Simple as that, okay? That is the ins and out of the Thorpe tube. Now, but this is another thing. If I'm traveling with a patient and he got to go to CT, right? I'm going to put this on a cylinder, an E cylinder or something. Would I rather have this one where the ball, because usually you got to lay the tank down. You ain't going to have a tank standing up in the patient's bed, right? It's going to be laying down. So if I have this laying down, then it's not accurate, right? That ball is just going to roll around. I don't know how much he's getting if it's laying down. So when we travel, we always use the, what's this? This gauge called? Bourdon gauge. You always want to use this type of regulator with the flow meter built in. That way, no matter how this is laying, it's going to give you an accurate pressure. Okay, it's going to give me an accurate pressure and flow. Okay, whatever flow I turn it on, that's what he's getting. And the pressure that's in the cylinder doesn't change because of the way I got it laying. Okay, so to travel, the regulator of choice for traveling with a patient would be the Bourdon gauge. Okay, so let's talk about the Bourdon gauge, and I think that will be it for this lesson. All right, here it is again, uncompensated. Now, we talked about the compensated Thorpe tube. Uncompensated is simply the opposite, okay? The needle valve proximal to the float. That's not true, right? If that happens, it's uncompensated. If that needle valve is before the flow, it's uncompensated, right? Because the needle valve should be distal to the flow. So the flow meter reading will actually be lower than what's being delivered if back pressure is present. Then you have something called a kinetic flow meter, which you're not going to ever see. All right. A kinetic flow meter is simply looks just like the Thorpe tube. It looks just like this, except it has a plunger in there. You know, like a syringe has that little rubber plunger inside. That's what it looks like. Okay. It's a plunger instead of the ball. It's a little plunger. That's the only difference between a kinetic flow meter and the regular Thorpe tube. All right. All other areas of the Thorpe tube apply except for the float. The float won't be a little metal ball. It would be a little rubber plunger. And I've never seen one in all my years of respiratory. All right. Lastly, the board-on gauge. The board-on gauge, and we'll be done. The board-on gauge, this is important. This first, number one, you need to make sure you highlight this. The board-on gauge measures pressure, but reads flow. Okay, it measures the pressure, right? When I hook it up and turn that cylinder on, it's going to tell me the pressure, right? The board-on gauge is going to tell me the pressure, whether it's the big one like this, right, where I can see the pressure, or it's the smaller one. It measures the pressure, but reads what? The flow. That's a statement you better know. The board-on gauge measures pressure, but reads flow, okay? The flow delivered to the patient is less than flow shown on the gauge if back pressure is present. And it works what? In any position. That's why we want to use that when we travel. Because most cylinders are stored up under the gurney, right? And there's usually like little pockets where you can put the E cylinder, okay? Nobody's traveling with an H tank in the bed, okay? It's the E cylinder. And there's little slots on the back of the bed or under the bed that are already made for the E cylinder. And so since the board-on gauge works in any position, that's the one we usually use when we travel, okay? Now, they're phasing these out, really. The cylinders they have now already have these built on, okay? They have what's called grab-and-go cylinders, all right? They got these little grab-and-go cylinders that look like this. Grab-and-go. Oxygen cylinder. We found one that's good. Yeah, here we go. All right, so let me save picture as. All right, so this is a grab and go here. Let me share my screen. Okay. Here's the grab and go. See that? This is an E cylinder, an E oxygen cylinder that already has, look, it has the flow meters up here. You can't really see it because I had to make it bigger. But see this is LPM, liters per minute right here. And if you can, it's on off right now. I turn this knob up here to this way, and it'll be 1, 2, 4, 6, 8, liters per minute. And it's already built on. So all I have to do is grab it and stick my nasal cannula right here. There's a little opening right here where I can stick my tube in right there and just turn it on. I don't have to put on a flow meter. I don't have to put on another regulator, right? It's already built in. And this right here is the board-on gauge. Lets me know how much is in the cylinder, okay? This is what we use 99.99% of the time, okay, guys? So that's what you're gonna see the most. They also look like this one, okay? They have some digital ones, all right? They have some digital ones. Let me show you the digital one. Come on now. Save image as. All right. Share. This one. See this one? This is already built on, right? And it has the digital. That's when you're getting fancy, right? You're not gonna have this many. I've never seen a digital one. But notice how it's, what's this right here say? No what? No, not liquid. This is the sign for this. Come on in your car sometimes. Start flashing.
Oh.
Oil. when your oil is low or something's wrong with the oil, this little symbol will flash up without the X, but the little oil symbol, right? This is telling you no oil because oxygen supports what? Combustion, right? And oil is a product of petroleum jelly. Look, on this one, you can kind of see some of the markings, right? Some of the markings on, I don't really know who this Luxor might be the manufacturer right here. But you know, you can't really see it, but you see markings, right? You do have markings on your E cylinder, all right? So that's another grab and go, right? Little grab and go cylinders. So we use those a lot, okay? All right, so the bourdon gauge measures pressure, but reads what? Flow. Flow, works in any position. That's what we want when we travel, okay? And usually it'll be the grab and go one. Now, instead of all of this, you see all this can be hard to lay all this in the bed, right? So now they just use the grab and go joints, okay? All right, this is the inner workings of a bourdon gauge, kind of showing you the pointer and stuff like that. It's just kind of showing you what it looks like on the inside, okay? Now, use of oxygen flow meters with helium. Remember I talked about helium. Sometimes we use a mixture of oxygen and helium, all right? And the reason is because sometimes you have airway obstructions, okay? So if you have cancer, say a patient has a tumor in his left main stem bronchus. You might have a tumor in your left main stem bronchus, all right? That is occluding the oxygen flow, and you can't get the oxygen to the lungs. So you got your trachea, this will be the right, and then you have your left, right? This is the left, this is the right. Now, what if I have a big tumor right here? Right? Look at that. See that tumor? Can y'all see that on the screen? Do I need to get closer?
I can see it.
Okay. So if I have a tumor right there, now the oxygen that I'm breathing in, see the oxygen coming in is going good over here on the right, right? But coming in here is getting tied up, and just a little bit is getting through. Okay? I know you probably can't see that though. I'm gonna do this right quick to show you what I'm talking about. See how the oxygen is getting held up right here, and only a little bit is making it to the actual lung, all right, because of this tumor here. All right, so what happens is we can give some heliox, okay, which is helium mixed with oxygen, and that would be what would happen if I mix that up. Now the heliox will bring all of it up above the obstruction. It lifts the oxygen up above the obstruction so it can get on down past it into the lungs, okay? That's why we would use heliox, all right? And we have different mixtures. We can do a 70-30, or we can do a what? 80-20, okay? We can do 70-30 heliox or 80-20, depending on the severity of the obstruction, how big it is, right? Instead of, if they're not able to go in and surgically remove it, then they can use heliox, okay? So here's the heliox right here, either 80-20 or 70-30, okay? 80% helium, 20% O2, or 70% helium and 30% O2, okay? That's what we can do. Now, one thing to remember on heliox, because of the less density of helium to oxygen, the flow will be 1.8 times what you see on the meter reading, okay? The flow will actually be a little higher than what you see because you're mixing helium with it. So for instance, if you have a 80-20, right? If you have an 80-20 heliox mixture and you have the patient set on 2 liters, how much is he actually getting? The flow will be 1.8 times more than the reading. Okay, so if you have on a 80-20, on a 70-30, it'll be 1.6 times more. Okay, so 80-20 on an 80-20 mixture, and you have it set on 2 liters, how much is he actually getting? How much is he actually getting? 1.8 times 2. He's going to be getting 1.8 times more than what you have it reading at. 3.6. So he's getting about 3.6 liters per minute overall. Okay. What if he has a 70-30% mixture? Then and he got it set on 2 liters. What would he be getting then? About 3.2 liters. Okay. So that's what you need to remember, because they might say a patient, Mr. Johnson, is on a 70-30 heliox mixture, and he had it set at 3 liters per minute. How much flow is he actually getting, right? You got to know that 70-30 is 1.6 times more than that 3. So it'd be 3 times 1.6, which is what? 4.8 liters per minute, okay? Why do we use heliox? To help lift the oxygen or the gas up over a tumor or an obstruction in the large airway, not the lower airways, the larger airways, okay? That's it. That is it for oxygen cylinders and gas physics. Go back, look at, all right, we had a little pause there for a minute, but go back and look at your reading, do your reading, and your these lectures. Look at the lab over the weekend, okay? Look at the lectures and the lab over the weekend, okay? Do your reading and find out everything you can find out. If you follow the lecture and the notes and the PowerPoint, all this stuff is available for you. This will be an easy 100 for y'all. Like I said, it's not a lot of human interaction. Like there's not a lot of, well, this happens in the lungs and this. So it's just basically remembering the different bodies that are affiliated with cylinders, how to properly turn it on and how to properly turn it off, which you will be doing in the lab, right? But other little things like that, that's the kind of stuff that I'm gonna be looking for that's on the exam. If you can do that, that's not a problem. Don't forget Charles, Boyles, Gay-Lussac, right? Don't forget those. Look at the gas laws video if you need a little help, looking at it, okay? Look at that. This, like I said, this should be an easy comeback for you, all right? This one here will be a nice little bounce back for you if you haven't done as well as you wanted to do. This test here should be a little bit easier for you to complete. It's not a hard test, all right? It's just simply the cylinders and the gas physics, all right? You can do this. Homework for this weekend. What are the homeworks for this section? Was it 1, 2, 3, 4, and 5? Okay, we haven't done any of those. I want y'all to do homeworks 1, 2, 3, 4, and 5 over the weekend. All right, and just take a picture of them and upload it to me the best way you can. But you got now, tomorrow, and Sunday to be doing this homework because I haven't assigned any of them to you. Okay, so now is the time to do them. Don't forget, if you do 1 and 2, but you don't do 3, 4, and 5, you're gonna have points off. They're 20 points apiece. All right, 20 points apiece. So make sure you do them. Also, don't forget them little 5 questions from the lab book to have ready for you on Monday. When you come in, you need to have those done so that you can get into the lab. Be dressed out. Don't forget your stethoscope. Don't forget your watch, your nails, all the dress code stuff. Don't come in with long pointy nails and long eyelashes and all that. You got to be in dress code on Monday, okay? We're going to have your 8 to 12 group and your 1 to 4 group. I don't care which one you come to, all right? But if you come to one, be on time. If you choose to do 8 to 12, be here at 8. If you can't be here at 8, you need to come at 1, because if you get here at 9, I'm going to send you back to wait till 1, because I'm going to be doing some teaching and letting folks check off. So I won't have time to go back to every party that comes in. He come in at 9. This one coming in at 10. This one popping in at 11. It's not a free time to come. It's 8 or 1. All right? Do those homeworks over the weekend, which will help solidify this information. If you find something you can't find it, then leave it blank, right? I'm not going through it with a fine-tooth comb. I don't want you to just put anything, but I don't want you to be stuck. I just can't find number 5, so I'm through. I'm going to give up, right? Just, if you can't do that one, skip it, right? That's fine. But do all 5 of them for credit. And the more you do it, the easier this test will be, okay? See you Monday, dressed out, either 8 or 1. You can let me know over the weekend which one I'm coming to. That's fine. If you forget to tell me, that's fine. I'll be here from 8 to 12 and then 1 to 4, all right? Make sure you complete that. Have a good weekend. Be safe. You know, the election's out there, so it might be some crazy things going on. Keep your safety. Watch your surroundings, okay? You got people that might do anything on either side. So be careful while you're out there. Wear your mask. Don't forget that. When election going on, people don't forget about Corona. Corona ain't went nowhere. So make sure you watch out. Be safe. I'll see you on Monday. All right.